it's a regular graph. You see all the vertices have degree 4. So the maximum, they all have degree 4, in particular the maximum is of degree, the maximum degree is 4. You can see it's sort of based vaguely on a pentagon. There's a pentagon around the outside. In that sense it's like the Peterson graph, but it's a bit more complicated. How many vertices are there? Well, there are the 5 of the outside pentagon. There's also an inner pentagon. That's another 5, and there are 2 more. So it seems that there are 12 vertices. And since there are 12 vertices, each of degree 4, that would be 48, but 48 edges, but each edge has 2 vertices, so it's 24. It would appear to be 24 edges. So you can look at it like this. There are the 5 edges around the outside pentagon. Each vertex of the outside pentagon has 2 edges associated to it. That's another 10. That makes 15. And then on the inside here we've got 9. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can think of this, if you like, as sort of 5 plus 10 plus 9. So that's consistent. So supposing this is a regular graph, so Brooks's the 2-part algorithm. So the 2-part algorithm remember, that's an algorithm to try and colour a graph in not more than delta colours. But because this is a regular graph, the 2-part algorithm is not guaranteed to do that. So the 2-part algorithm is not guaranteed. To colour in less than or equal to 4 colours. Okay, I want to colour it now. I want to do this graph. And I do the 2-part algorithm slowly. Then we do another example more quickly. So the 2-part algorithm, how many colours do you think it will take? Does anyone want to guess? You see, the problem is this is a regular graph. So wherever you finish up, we're going to order the vertices in a moment. But then you do the order, you colour backwards. But wherever you finish up, suppose we finish up at this vertex here, that degree is 4. So it could be that we need a 5th colour, because if things work out badly for us, these 4 vertices here, here, here and here, the adjacent vertices to the last one, they could all end up being different colours. Therefore we'd need a 5th colour. Okay? The 2-part algorithm works because you always have to start at a vertex that has less than the maximum degree, but with a regular graph you can't do that. So in fact, the best we can hope for before we start would be 5 colours in this case. But let's just apply the algorithm as an exercise for doing that. So first of all, it's a 2-part algorithm. So first of all, we order the vertices. We do a breadth first search, starting anywhere, to order the vertices. Now, since it's a regular graph, well, there may be some vertices special, that I don't know, but let's start at the top. Okay, and it might matter. Maybe if I didn't start at the top, I'd get a different answer, so I can leave you to try different vertices to start from. So if we start at the top, the idea of breadth first search, so let me remind you, if you weren't here, this stands for breadth first, because we sort of start from a given vertex and you sort of search widely, you don't go into depth. Breadth first search, and this uses the idea of a breadth first search. It works that way because it uses a queue rather than I'll just write Q like that, Q. rather than a stack. So we need to do a queue as I did last week, so let's just do that shorthand. So shorthand means that I start with 1, and then I look at the adjacent vertices. These aren't numbered anymore, so I have to put the numbers on myself. So it doesn't matter what order I use, let's go roughly from left to right here. So I make that 2, 3, 4, 5. Okay, so that means that I'm putting on the queue vertices 2, 3, 4, and 5. And then I've done 1. Then I look at vertex number 2, and I look at the ones which haven't been numbered already. I have to remember where I got to. So I got to 5, so I'm going to go, let's go top to bottom. So this would be 6, 7, 8. I've done 2, I've got to 8. So I then look at vertex 3. There are two vertices not yet visited. One says unvisited, not yet numbered. So that would be 9 and 10. Let's go from left to right. There are only 12 vertices, it's not going to take us very long. So we've done 3, we now look at vertex 4. So this has one adjacent one there that hasn't been visited, so we make that vertex 11. Now we go to 5. From 5 we can actually see the missing vertex number 12. So now we should have everything. Well, we've done it in order, so we've got everything. So that's our queue. Of course, the numbers don't mean much on them by themselves because it's where we put them on the picture that matters. In this case, the numbers are in order in this case because we didn't already have a numbering of the vertices. Remember, the point about this queue here is that any vertex like 7, we got 7 because it was adjacent to 2, but because the vertex degree is 4, there will only be 3 vertices, at most 3 on the right, which is adjacent to. So most of the time we can use, when we go backwards from 12, we would expect to only need 3 colours. The question is what happens when we get to the last vertex, because the last vertex has 4 things in the queue after it. So that's the problem. It has 2, 3, 4, 5, as I said before. That means if these end up coloured differently, we need a 5th colour for vertex number 1. Okay, so let's just do the colouring and see what happens. So we colour in reverse order. Here it doesn't actually matter because I haven't made a special choice of the first vertex, but the idea of the algorithm, you should always learn to colour in reverse order if you were able to make the first vertex of lower degree. So let's say this reverse order here, it doesn't really matter, but it's essential when, if we are able to choose the first vertex of the queue with degree less than delta. Here we can't do that because it's a regular graph, but if we were able to do that, we must always colour in reverse order. So let's do the colouring. I'll do it on the graph. Well, I'll do it both on the graph and underneath these numbers. So we start in reverse order. So we start with vertex 12, which can be alpha. Now, if you're doing this properly, you should also write, maybe below each vertex here, the adjacent vertices, so you don't make a mistake. But here I rely on the picture and you to check me. So we now go to 11. Well, 11 isn't adjacent to 12, so that, by the rule, that has to become alpha as well. That's coloured alpha because you take the lowest colour. We're using colours alpha, beta, delta, alpha, beta, gamma, delta, and so on. So 11 can be alpha. 10 has to be beta because it's adjacent to alpha. 9 is not adjacent, I think, to anything, so that has to be alpha. 8 has got 2 alphas, so that can become beta, has to become beta. 7 has alphas only, right, so that can also be beta. Shout if I make a mistake. 6 has got an alpha and a beta, so here we do need a gamma. 5 has an alpha and nothing else, so 5 can have a beta. 4, it doesn't take long, you should see, to do this. 4 has got an alpha and a beta, no gamma, so it has to be gamma. 3 can be a gamma, since it's got a beta, an alpha and a beta. It's only got 3, you see, because of the way we did the Q, there's never more than 3 adjacent vertices. So we've got beta, beta, alpha, so 3 can be gamma. 2, again, it can only have 3 adjacent vertices. We might need a delta, but we don't. Beta, beta, gamma, so we can make 2 alpha. And now the key point, what have we got? We've got alpha, beta, gamma, so 1 has to be delta. Is that right? Have I done it correctly? So I did succeed in using 4 colours. I didn't think I would, actually, because I did this morning, but probably I took a different ordering. When I chose the adjacent vertices, I took a different ordering. I needed a 5th colour. But if I haven't made a mistake, you do only need 4 colours. The key thing is that when I came to do 1, although it's adjacent to 4 vertices for the first time, it turns out that 2 of these vertices had the same colour, so we're okay. Okay, but had this been a delta, then of course I would have needed epsilon there. Okay, any questions about that? So we were lucky, we did it in 4 colours. Let me do the same example. It sort of lost a bit of its punch because I was expecting that to need 5 colours. Let me take the same graph and make it regular, cut the paper so I can get rid of one edge. Okay, so here's the same graph. Any questions about this before I remove it? Yeah. Sorry?
Why can't you do 3?
Well, it turns out this graph cannot be coloured in 3 colours.
Why is that?
I can't prove it, it's just a fact that the chromatic number is... I mean, what do you know in general? If the vertex degree is delta, the theorem only tells you that the chromatic number is less than or equal to delta. So this graph is a rather special graph, and it was chosen partly so that it can only be 4 coloured. Okay, so remember, this tells you by Brooks's theorem, which is more powerful than the regularity thing. Brooks's theorem tells you that the chromatic number, since this is neither a complete graph nor an odd cycle, we know that the chromatic number is less than or equal to 4, but there's nothing to tell me it's 3. Okay. I'll check this in a moment on the computer, and we'll check that I'm not telling a fib, that the chromatic number is actually 4. Remind me to check that. Okay, but if you fiddle around, I claim you'll never do it in 3 colours. Whereas what are the other graphs? The Peterson graph is 3 colourable, I think. The Grotch graph is not, I think, 3 colourable, if I remember correctly. Anyway, here's the same graph without a vertex, with 1 edge missing. So this is Chvatal minus 1 edge. Well, I'm going to do exactly the same thing that I did, but I'm just not going to write down any tables. So you see, you can just do this on the graph. So there are no numbers yet. So let's just put let's take a different vertex. See, well, no, sorry, I must start from one of these 2 vertices. Let's start from this one, because these have degree less than the maximum. So the maximum is still 4, but it's no longer regular, because I've got 2 vertices of degree 3. So you start from a vertex, you start from a vertex of lower degree when you do the 2-part algorithm. Start from vertex of degree, in this case 3. There are 2 of them, once I remove 1 edge. So let me just do the number. I just do exactly the same thing as I did before, so just check that I'm doing it correctly. So I number the vertices using a breadth first search, taking in arbitrary order the vertices adjacent to 1. Then I go to 2. You have to be careful. Now I've done 1, so I'll put a line through that. And then I go to 2. 2 is adjacent to 1. I've got 3 more vertices, so I've got to 4. Then you have to be careful now where you've got to. So 5, 6, no, I don't know what the 1 was doing, that means I changed my mind. 6, 7. Then I've done 2. Now I go to 3. I've got 7, so this becomes 8, 9. Then I go to 4. I've got to 9. There are no new vertices adjacent to 4. So I go to 5.
There's 1.
There's 1. So where's... Oh, there's this one. Quite right. So what's that? A 10? Right? That's a 10. I've done 4. So I now go to 5. The missing vertex, we've got 5. I've got this one is missing, so that's 11. Okay, we've done 5. Now I go to 6. And I can put this as number 12, and I've done them all. Right? So, a bit hairy. You just remember cross things out. Don't recommend doing it without some sort of table. Now we colour in reverse order. Okay, we must colour in reverse order. So, now colour in reverse order. Is that all right? You're happy with my numbering? Any objections? Colour in reverse order, so we start with 12. So, I'm going to cut it. Okay, I use the same pen. So this is alpha. 11 has to be beta. 10 can be alpha. 9 can be beta, has to be beta. 8 not adjacent to anything, so it can be alpha. 7 can be beta. 6 adjacent to only alphas, remarkably, so that can be beta. 5 adjacent to alpha and beta, so it has to be gamma because of this alpha here. 4 I've got an alpha and a beta, so this has to be alpha, alpha, beta. This has to be a gamma. 3, beta, alpha, beta, has to be a gamma. 2, gamma, beta, beta. 2 can be alpha. And finally, number 1, we've got a gamma, an alpha. And so I can do that in 3 colours, right? I can put a beta there, something like that. So this is 3, apparently this is 3 colourable. It's not the original graph, I took one edgewise. Okay, so this is better than you might expect. So it seems that this is 3 colourable. I was lucky again, probably the order I chose was lucky. And that's better than you might expect from the 2-part algorithm, because the 2-part algorithm will only guarantee, if you do these things, to have less than or equal to 4. So this is better than we might have expected. So it did work out for the best than I expected.